So today's module is about dental cements, which have various restorative applications and also as luting agents, and they form a very important part of the materials available in dentistry. So today we are going to cover the essential definitions, the ideal requirements, classifications for different cements, the uses, and then individual cements in detail. Compomers and then uses of cements as pulp protecting agents and atraumatic restorative techniques. So to start with, first of all, we will look into the definition. So what is a cement? Cement is a substance that hardens to act as a base, liner, filling material, or adhesive to bind devices and prostheses to tooth structure or to each other. In general usage also, what we refer to as cement is a substance which is setting by a chemical reaction to a hard set mass, and then you can use it for different types of applications here as a base, that is underneath a restorative material, as a pulp protecting agent, as a liner, as a restorative material in itself, or as an adhesive, that means to lute, to bind things together. So you can use it to bind different types of appliances or prostheses like a full coverage crown or a veneer to the tooth structure. So is the definition of a dental cement. So what all do we have to understand about it? One is the acid-base reaction. Acid-base reaction means it's a chemical reaction between a compound which has hydrogen ions, replaceable hydrogen ions, and the other substance will have the hydroxyl ions. So one with the hydroxyl ions will be the base, and which is donating or losing the H ions will be the acid, and the resulting reaction will lead to the formation of a salt and water. Then working time. Working time is very important concept because this is the time that you'll get from the starting of the mixing of the cement to the time at which the viscosity of mix is still low enough to flow readily under pressure and to form a thin film. Not just to form a thin film, but also to adapt to the cavities, surfaces, or the walls properly, like if we are using it for restoration. So what will happen is, as we start mixing the two components, that is the acid and the base, the reaction will gradually make the mix thicker. That is how it is going to achieve its setting. So then it is no longer you can adapt it, condense it. So that will mark as the end of the working time. Okay. Then we have setting time. Setting time is a time elapsed from the start of mixing to the point where the mixture reaches its desired hardness or consistency. After that, you will not be able to work on it or shape it further without using any other tools, like you may use a blade or a scalpel or a file to redefine it, but then on its own it has reached sufficient hardness to hold whatever shape or contour you have built into it. It is not going to slump. So that is what is meant by setting time. Then luting agent, viscous material placed between tooth structure and a prosthesis that hardens through chemical reaction to firmly attach the tooth structure and prosthesis. It is just going to be an adhesive link agent which is going to bind the prosthesis to the tooth structure. Then you have a base. So base is basically a pulp protecting agent, layer of insulating, sometimes medicated cement placed in the deep portion of the preparation to protect pulpal tissue from thermal and chemical injury. So basically, this is what we have discussed. There's a powder component. The liquid component is usually the acid component, which has water also there, which is helping in ionization of the acid there. Then the two mix will initially be like a paste-like or a flowable consistency. Gradually, as the chemical reaction progresses, it will harden to a rigid solid, which can be used for different types of applications. So this is in general about the dental cement. So typically it's a powder liquid system. Liquid is an acid, powder is a base insoluble in oral fluid. When mixed together, you get the acid-base reaction forming the conventional cement. Why it has been called as conventional cement? Because now today you have bioceramics, you have resin cements, which will not work on this acid-base reaction. That is why we have called it as conventional cement. Then we come to the ideal requirements. Ideal requirements are most, say, 60-70%. They are common to all the biomaterials that we are using in oral cavity, that it should be non-toxic, non-irritant. It should be able to protect the pulp, antibacterial, so that any residual microorganisms which have been left after your cavity prep can be taken care of. There should be adhesion between the cement and tooth tissue. Now, what is the role of adhesion? Adhesion is important for preventing leakage of substances at the interface, number one. Secondly, it is also very important for transfer of stresses from the tooth to the restorative material and restorative material to the tooth structure. So the bond determines the longevity of the restoration, or you can say the weakest link. The tooth has good strength, the restoration has good strength. But what is the weakest link? It is the junction between the cement and the restorative material. Then it should have additional requirements, or should fulfill additional requirements like an adequate working time. It must develop strength rapidly, good flow characteristics so that there are no voids and it is adapting to the cavity walls. And it should be insoluble in fluids and saliva. Now, when we are using it as a luting agent, that is to bond a prosthesis or an appliance to the tooth structure, then it should have low film thickness. It should have ease of use, radio opacity. It should have good aesthetics and adequate working time at mouth temperature. Okay, so these are additional requirements for luting agent, that it should have a low film thickness so that an accurate fit can be maintained. Good aesthetic properties, no staining or discoloration, ability to take and retain a smooth surface finish are the additional requirements when the cement is being used as a restorative material. Now, classification. Classification can be of different categories depending on their usage, depending on composition, bonding mechanism. Lots of classifications are there. So here what we have is a basic classification depending on the matrix forming species or how the cement is going to set. So phosphate-based cements are zinc phosphate and silicophosphate. Eugenolate or phenolate-based cements are zinc oxide eugenol and calcium hydroxysalicylate. That means they are going to set by chelation reaction. Then you have polycarboxylate-based cements, zinc polycarboxylate and glass ionomer. And finally, resin-based polymethyl methacrylate and dimethacrylate cements. So this is based on the matrix forming species. Again, the same thing based on composition, which is the phosphoric acid base, organometallic chelate base, polyalkanoid cements, and resin cements. Then what is here? We are having two components of a cement. One is the powder component and one is the liquid component. So what is seen in blue is mainly the powder component. So if the powder component is zinc oxide and it is reacting with different types of liquids. So you may have eugenol as your liquid, which will give you zinc oxide eugenol. Same zinc oxide reacting with polyacrylic acid will give you zinc polycarboxylate cement. And when combined with phosphoric acid, it gives the zinc phosphate cement. Now what we have done is we have changed the composition of the powder phase also. From zinc oxide, we have shifted it to a glass phase, fluoride containing aluminosilicate glass. Now when this glass is reacting with polyacrylic acid, it gives us glass ionomer cement. And the same glass reacting with phosphoric acid gives us silicate cement. So this is indication of the powder component, and these are the available liquids which are reacting and giving different types of dental cements. According to usage, this is a classification given by Skinner's, where according to primary and secondary usage, the cements have been classified. We'll just go through one example to understand. Example, zinc phosphate. The primary usages are the luting agent for restorative and orthodontic appliances. Secondary uses are as an intermediate restoration and thermal insulating base. So primary use means which is the preferred or most desirable usage. The other is the it can also be used as will be known as the secondary usage. So glass ionomer cement, it is having the advantage that it is tooth colored. So that is why it can be used as an interior restorative material, as a luting agent, and as a cavity liner because of its pulp protecting properties. In secondary usage, it can be used as a pit and fissure sealant and thermal insulating base. Okay. Then again, as I explained to you already, those having the acid-base reaction as the setting mechanism are called as the conventional cements, and those based on polymerization chemistry are called as resin-based cements. Then we have luting cements, which can again be temporary and permanent. Then you have pulp protecting or cavity sealers, cavity varnishes, liners, and bases. Then as restorative material, again, depending on the time for which it is intended to give the clinical service, it will be temporary or permanent. Other uses are as a root canal sealer, calcium hydroxide based cement, and as a bite registration material. Now we are going to discuss the first important cement, which is considered as the gold standard, that is the zinc phosphate cement. You all are a little bit familiar with this cement, having manipulated it in the practical classes. So zinc phosphate cement is oldest cement with longest clinical track record. It serves as standard for comparing with the newer systems. It has a wide range of application from cementation luting to their use as a cavity liner or base. Supplied as powder liquid, which gives us a mass of cement having desirable physical properties when mixed. So this is the powder composition, the major component being zinc oxide powder with different types of modifiers added to it for radio opacity, as an inert material, as the second matrix forming phase, magnesium oxide is there. All these are the powder components. So functions mean zinc oxide is the principal ingredient, magnesium oxide controls the temperature of the calcination process to which the cement is heated to fuse all these powder components, and silicon dioxide also aids in the calcination process. Then bismuth trioxide smoothens the mix and lengthens the setting time. So anything which is increasing the setting time will help you with the working time. And then we come to the liquid. Liquid is mainly phosphoric acid. 38.2 weight% phosphoric acid, which is the main component which is going to react with your zinc oxide. Then what is this buffer? Buffer is zinc phosphate combined with aluminium and zinc. So whenever you have the byproducts of the reaction already present, it slows down the reaction rate. That is why zinc phosphate combined with aluminium and zinc is called as the buffer. Then you have aluminium and zinc and water, which controls the ionization of the acid. That means in the presence of water only, H ions can be released. Then we come to the setting reaction. So consider these are the drops of the liquid containing phosphoric acid, which you are mixing with the powder, which is basically zinc oxide in composition. So when these H ions from the liquid are going to add on this, then they are going to displace the zinc, Zn plus ions from the powder particles. Now this combines with the phosphoric acid which is there to form zinc aluminophosphate gel. So where this gel will be? This gel will be surrounding the unused zinc oxide particles. So these unused or unreacted zinc oxide particles will be surrounded by the zinc aluminophosphate gel. Now in this process, there is liberation of heat. That means the reaction is exothermic. When the liquid is mixed with zinc oxide particles, the H ions present in phosphoric acid displace the zinc and aluminium ions from the powder portion of the zinc oxide. These react with the phosphoric acid and form zinc aluminophosphate gel. So now these are the unreacted particles. What is the importance of this unreacted particle is that it will be a major contributor to the strength of the cement when you are using it in the clinical applications. Okay, so as we have seen that there was liberation of heat. So it is an exothermic reaction. Addition of water can accelerate the reaction. Why? Because water is the medium of ionization. Loss of water can lengthen the setting reaction. It will not set properly, and the matrix formed will also not be of good strength. Higher sintering temperature reduces reactivity. Now, this is not in our hands, but yes, the manufacturer has done sintering at a higher temperature, then you will have more working time and it will take more time to set also as the reactivity is reduced. Final particles react quickly due to increase in the surface area. Usually, the cement that is used for luting will have finer particle size as compared to the cement which is used for restorative purpose. So that it will give you a thin film. So now how do you manipulate it? First is you take a cool glass slab but not below the dew point. What is dew point? Dew point is a temperature at which the atmospheric moisture condenses to form droplets of water. So if we have a very cool glass slab and the moisture present in the air condenses on it, then your water powder ratio will change. That is why they said that you have to take a cool glass slab but not below the dew point. Then just before you are starting with your restoration or luting, that time you have to dispense the powder and liquid. Now, how much powder, how much liquid is normally specified on the pack of the cement that you're buying. And again, depends upon what is the intended use, whether you wish to use it for restorative mix or you wish to use it for a luting consistency. So accordingly, you have to take the powder liquid ratio. Initially, mix smaller increments of powder with liquid. Keep on adding larger increments till desired consistency is reached. Now, because if it is it's an exothermic reaction, if you mix a lot of amount in one go, then you might shorten the available working time for you. So say this is the glass slab in which the increments have been made out of the zinc phosphate cement. Now we are taking increment one by one and spatulating it on the glass slab with the help of a stainless steel cement spatula. A large surface area has to be used for this purpose. Then you can add more powder to it and keep adding more increments there. As you can see that a wide surface area of the glass slab is used. Spatulation is done with each increment for 15 to 20 seconds. This is because we want to dissipate the heat which is being generated or liberated. More the surface area involved, better will be the dissipation of heat. If there is buildup of the heat, again setting reaction will be accelerated and you will not be getting sufficient working time. Now this is showing what? This is showing the consistency. How do you check? Okay, now my mix is ready for luting. I do not want to add more powder to it. So for luting consistency, if you try pulling your cement spatula from the surface of the glass slab, it should form a 1-inch string. That is what is called as luting consistency. For liming consistency or restorative purposes, it has to be a ball-like consistency where the powder liquid ratio is going to be higher as compared to a mix for luting consistency. So accordingly, you will get either a stringy kind of a consistency for luting or you will get a pie dough or ball-like consistency for restorative applications. Now coming to the properties. Properties are defined by the ADA specification number 96. So working time is 3 to 6 minutes, setting time is up to 8 minutes is all right. Powder liquid ratio 1.4 milligram powder mixed in 0.5 ml of liquid. Comprehensive strength is 80 to 104 megapascals. Tensile strength is very less. Modulus velocity is good. And there is a moderate pulp response. Now, this is very important in understanding because we are using it as a base or pulp protecting agent. But whether to use it or not or shift to some other material will depend upon your remaining dentin thickness. Zinc phosphate cement, because of presence of phosphoric acid, has a low initial pH. And that low initial pH is the reason for the moderate pulp response or moderate pulpal inflammation. So how do you extend the setting time? How do you extend the setting time? Whenever the reaction rate slows down, there will be more setting time available. So reducing the powder liquid ratio, but the cement will become weak. Mixing on a cool glass slab, but without moisture is all right. Mixing over a large surface area, mixing in increments. Again, the heat buildup does not take place and you can incorporate more cement into it. And you will have a higher setting time also. Adding the increments slowly. Then we'll look into the effect of manipulation variables on properties. Now, the calcination temperature, the powder size, the composition, exact, it is not in our hands. So, what we can do is, if we decrease the powder liquid ratio, then it will increase the setting time. However, other properties will become compromised because the unreacted ZNO, the particles which were there, and that concentration will reduce. Increased rate of powder incorporation, again, the heat will not dissipate, and ultimately you will have less time. So increase mixing temperature and water contamination. So all these will lead to reduction in compressive strength. Why that is happening? Because less the amount of powder that is incorporated into liquid, lesser will be the strength. And also the setting time is coming down. Okay, but solubility, initial acidity, film thickness will increase if we are not properly following the powder liquid ratio. So when we come to the biocompatibility means that there should be no harm to living tissue. But the only drawback with zinc phosphate is that the acid can penetrate into dentin and tubules and irritate the pulp. Thinner the mix, more is the acid content. If we are using it as a luting agent as compared to restorative agent, in luting there are higher chances of pulpal irritation as compared to restorative consistency. So pH of cement is liquid is 2. 3 minutes after mixing, it comes up to 4.2. 1 hour says 6, and almost 48 hours after it comes back to 7. So this is one of the cause for the pulpal irritation. You have a freshly cut dentine surface, and then you're going to place something which is highly acidic and has a initial pH of 2 to 4, then it is going to cause some sensitivity. So what are the clinical applications? Luting agents for inlays, crowns, bridges, and orthodontic brackets, base, and provisional restoration. These are the clinical applications. Now, what are the modifications? Modifications are some minor modifications with addition of other ingredients to the zinc phosphate powder component. One is that you can add a silver-based cement to make it bactericidal. Again, copper oxide has been added to make it red or black. Fluoride cements have been tried adding to the zinc phosphate cement, which increases the solubility and lowers the strength. Then again, zinc silicophosphate cement has zinc phosphate plus silicate. But anyways, none of these are much utilized now. Now we come to the zinc polycarboxylate cement. Now, one thing important to remember is that though zinc phosphate is a gold standard for comparison of other cements, it does not have any chemical adhesion to the tooth structure. It is only mechanically retained, whereas this polycarboxylate cement has the advantage of forming a chemical bond to the tooth structure. So it was the first adhesive cement which was introduced. Okay. Polycarboxylate cement is also called as polyacrylate cement. Why? Because the functional group is COO minus, which is also called as polyacrylate or polyacrylic acid cement. So it was the first adhesive cement to bind to the tooth structure and metal. It is more biocompatible than zinc phosphate cement. It has moderate strength and moderate solubility. Okay, excuse me. So now, again here, the major powder component is zinc oxide, followed by magnesium oxide, aluminium oxide, bismuth oxide, and stannous fluoride. What is a liquid now? Liquid has undergone major change. There is no longer phosphoric acid. It is 40% aqueous solution of polyacrylic acid or an acrylic acid copolymer with other organic acids like itaconic acid. Tartaric acid can also be there. So what does this do is it increases the molecular weight of the polymer when we are copolymerizing it with other acids like itaconic acid. It increases the molecular weight of the polyacrylic acid and provides viscosity to the liquid. This viscosity is the reason for the mild pulpal response. Consider that there is an open dentinal tubule. Smaller molecule of acid like phosphoric acid can easily diffuse through it and reach the pulp to cause irritation, but a heavy molecular weight polymer will not diffuse that fast towards the pulp. So that is why there will be lesser chances of pulpal irritation. Then we come to the setting reaction. Again, this is the liquid which is coming in contact with the powder or the basic component. Now liquid this time has polyacrylic acid. Again, H plus ions are going to be released. These H plus ions react with the zinc oxide powder or the core powder particles and release zinc ions. Then there will be kind of a cross-linking between the various polyacrylic acid chains, and then it is going to set to a hard mass. So the powder is rapidly incorporated into the liquid in large quantity as opposed to the incremental approach that we were taking for zinc phosphate cement. In glass ionomer cement, the powder is rapidly incorporated into the liquid in large quantity. Powder liquid ratio is 1.5 part powder to 1 part by weight of liquid. Mixing time is approximately 30 seconds. The mix should still be glossy when taken and applied on clean, dry cavity. The reaction is thixotropic. That means it becomes gradually thicker or more viscous, but when you apply pressure on top of it, it is going to flow. That is why it is called as the reaction is thixotropic. So the polyacrylic acid is believed to react with calcium ions via the carboxyl group or the COO minus group. The addition depends upon the unreacted carboxyl groups. That is why we need to have the mix in a shiny state. So that shiny state tells us that there is still free acid available for forming a chemical bond to the tooth structure. Bond strength is greater than with enamel as compared to that of dentine, obviously because dentine has more organic material in it. Working time is 2.5 to 3.5 minutes. Setting time is 6 to 9 minutes. The powder liquid ratio is 1.5 powder mixed with 1 part of liquid. And these are the other parameters. As you can see that solubility is really less, 0.06 weight by weight percent, and the pulp response is mild. This is important that the pulp response is mild. Then the polycarboxylate cement, pH of liquid is 1.7, but it is rapidly neutralized by the powder. pH 2.5 minutes after is 3.42, and within 48 hours, the pH increases to 6. pH rises more rapidly as compared to zinc phosphate cement. Why is that? Because of the large size of the polycarboxylate acid molecule, which limits its diffusion through the dentinal tubules. So what are the uses? As cementation for inlays and crowns, used as a base, as a temporary restorative material to lute the stainless steel crown in pediatric patients. Clinical consideration. What are the advantages of this polycarboxylate cement? Fluoride is released from the cement in small fraction as compared to GIC. The mixed cement may adhere to these instruments made of stainless steel. So use your alcohol as a releasing agent. Clean instruments before the cement sets. It adheres to the instrument and then remove in boiling sodium hydroxide solution. Number one is that you should be aware of the precautions to be taken. That is, you should use alcohol to clean the spatula or whatever is being used for mixing, and it should be used as a releasing agent. Okay. And if it adheres to the cement, then it can be used in cleaned by using a sodium hydroxide solution. Then we come to the silicate cements. Silicate cements are now obsolete. It is one of the oldest cement, no longer used because it was initially only tooth-colored restorative material available, so that's why it was used. Now the composition is almost similar that you will see for the zinc oxide or the zinc oxide based cements you have already done. Now these are the glass particle based cements. So you have silica, SiO2, alumina, sodium fluoride, sodium aluminum fluoride, and calcium salts, which again will react with the aqueous solution of phosphoric acid. So there will be formation of calcium free radicals and aluminum free radicals. In the core, unreacted glass particles are present embedded in the aluminosilicate gel. So anywhere there will be unreacted particles surrounded by an amorphous phase or the matrix. Then we come to the properties. Now with this silicate, the downside was the severe pulpal response, number one. And second, it did not have a very good clinical surface. There were lots of complaints about it getting dislodged or fractured, so that's no longer used. Now, what is the advantage of having this silicate bath? It had fluoride release. So this fluoride gives a lot of anti-carcinogenic properties, not only to the tooth structure, but also to the surrounding tooth structure where it comes in contact. Then you have zinc oxide eugenol cement. So lower strength than zinc phosphate, but it has a sedative effect. That eugenol, which is there, relieves pain. That is called a sedative effect. It's used as a temporary filling. pH is 7, so it is least irritating to the pulp. Non-eugenol cements are also available that are useful for eugenol sensitive patients. So eugenol is nothing but it is distilled or clean form of clove oil. And then we come to the composition. So composition has zinc oxide 69%, white rosine, zinc stearate, and zinc acetate. So the principal ingredient is zinc oxide. The brittleness of the said cement and plasticizer is affected by the presence of rosine and zinc stearate, while zinc acetate improves the strength of the cement. Okay, so the liquid is eugenol and olive oil. So what will happen is in the setting reaction, first zinc oxide will combine with eugenol to form zinc hydroxide. So zinc oxide reacts with eugenol, chelation takes place, zinc hydroxide is formed. Again, it is reacting further and leading to the release of water and formation of zinc eugenolate. That is happens only in presence of moisture. So paste or paste, how is this available? The zinc oxide eugenol cement, it can either be a powder liquid system or it can be a two-paste system. The two-paste system works by mixing equal paste together until you obtain a homogeneous color, something which you have already done in case of mixing your impression materials. For powder liquid system, you have to maintain the adequate water powder ratio. What are the classifications of zinc oxide eugenol cement? Type 1 as temporary eluting, type 2 as permanent cementation, type 3 for temporary restoration, and type 4 as a cavity liner. Now, how to increase the strength? Now, major drawback of zinc oxide is with the strength. So, it can be used as an intermediate restorative material or IRM. The powder contains zinc oxide with 10% to 40% finely divided natural or synthetic resin. The liquid contains eugenol, which may also contain dissolved resins, accelerators such as acetic acid and thymine. Now, what is the advantage of all this addition? The compressive strength has increased to 35 to 55 megapascals. So one way of reinforcing the zinc oxide eugenol cement is by forming the modified cement by addition of resin to it, finely divided natural or synthetic resin. Then you have ethoxybenzoic acid cement. It is slightly helpful for patients who have an allergy to eugenol. Then we have non-eugenol cements also. So this is a comparison of ZOE type 1, ZOE which has been reinforced with ethoxybenzoic acid, and lastly we have ZOA, which has been reinforced with the help of resin or polymer addition. So as you can see here, pulp response for all three is mild. Compressive strength increases whenever we are doing some kind of reinforcing or adding another thing which is stronger than the original zinc oxide eugenol particles. So what are the uses? As base, temporary and permanent cementation, endodontic sealer, and as a periodontal pack. So these are the uses of zinc oxide eugenol cements. Glass ionomer cement will be taken in detail in the next part of the lecture.